Hello everyone, welcome to this next tutorial, day 2 of a series related to data calibration. We are going to continue from what we left in the last day. So if you remember, we prepared two profiles where we applied the normalization to the to include the local continuum intensity, but also to apply the effect of limb darkening. So we assume, for example, there was a case of assuming a heliocentric angle of 0.71, and we renormalize the profiles, taking into account that effect. And we said that in the next day, so today, we were going to examine how the code changed the atmospheric parameters to compensate for this effect. So if we don't include this renormalization due to the heliocentric angle, probably our temperature at least will be off by a certain amount. So then today what we're going to do is to embed the profiles that we prepared. And also we are going, as we mentioned, we are also going to check how to remove undesired wavelengths, for example, telluric lines, just to improve the accuracy of the inversions. So then, as always, I'm going to share with you this folder that is day 2. Inside we have the two profiles that we created, and also we have additional elements to run the inversions. In this case, it's going to be SER to simplify things. And always I create a script with a very detailed information to just be able to follow all the steps, and eventually you can reproduce this in Python, for example. I will try to speak slowly because now I have braces, so my pronunciation is a bit different than normal, but I hope you will be able to understand me, and if not, just read the script, okay? So then, just as a very simple summary, remember that for running SER, we need to have SER installed. And then this means that we have to compile the code in a specific folder and create the executable ser.x. After that, we can point to this executable and run the code anytime. But for running the code, we always need several files. So always we need an abundance file. We also need a profile, that this is what we created before. So this SER 71, heliocentric 71, or SER norm, just assuming heliocentric angle equal 1. And then we will have the atomic parameters, that in this case is a file called lines.lt. So I'm going to open it here. And if you remember, it has this format with the index, the atom, the wavelength, and other parameters. And in this case, as we are going to invert only the two photospheric lines, I just simplified the file, just including these two entrances. But in principle, you can have a very large number of lines and call them if needed. Then we also need the wavelength grid, that if you remember in the last day, I mentioned that as we created already the wavelength grid and we had the sampling, we already had the information for creating this file. And what we are saying here is that we are going to deliver a profile file that contains only one index, that is going to be 1. But here in the wave grid, we are telling the code that in fact this profile corresponds to a blend of two lines. It doesn't mean that they are blended one on top of the other. It means that the whole spectrum that we provide in the profile file contains one or several lines. Okay, in this case it's 2. And then finally, we need two more things. So one is the control file, that it's here. I assume that you are used to see it. We are going to examine it in detail later, but just as a reminder that this is how the control file looks like. And then we need a gas atmosphere because we are going to do inversions. So it means that we need an atmosphere that's a starting point that then we will modify in a specific locations, the nodes or locations. And then from there, the code will get a good fit and the resulting atmosphere will be the solution that we want to use. So everything that I'm showing you is in this folder, day 2. So then Just as a reference, let's go to the configuration that we are going to use today for the control file. If you remember, we are using the atlas, so we have only intensity. So then this means that we are going to just give weight to the stocks I, and then we don't have Q, U, and B, so the weight for them is 0. So then the code will only try to fit stocks I. Here, as always, is the name of all the profiles that I mentioned before. And then here we have a number that is larger than 0. So it means it's going to run different cycles, inversion cycles, in this case 3. Then let's go slowly here. We have that for temperature, I think it's the main atmospheric parameter that we need for fitting an intensity profile, and in particular an average quite sun intensity profile like the one of the atlas. So then probably 235 is a reasonable configuration for temperature, and the rest of the parameters we can relax a bit the degrees of freedom. With, I think, velocity, maybe you can have some gradients. It's an average quite sun profile, but still it may be helpful during the inversion. And then I added one node for microturbulence, magnetic field, inclination, and macro turbulence. In the case of macro, in general, if you don't have the information of the spectral PSF, I think it's good to have it as a free parameter because it will help. In general, if the code does not need to apply any broadening of the synthetic profile to match the observed one, then usually the microturbulence will be small, but I think it's good to have it as a free parameter if you don't have the information of the spectral PSF. Then in the case of micro, I think it's always good to have one node, mainly when you have observations, because sometimes the code really improves the results using one node in micro. And then magnetic field strength and inclination. This is a bit tricky in the sense that maybe you don't need it. If it's quite sound, probably the magnetic field is going to be very, very, very weak. But in this case, I'm putting it as a free parameter, but only with one node. And this is because I'm using an initial atmosphere that is a general one that we created in the tutorials for SER, that has a specific field strength and a specific also inclination, and it's non-zero because it's an atmosphere that we will use for inversions. So if the magnetic field is, for example, 500 Gauss, and you don't have the magnetic field strength as a free parameter, then the code cannot make it weaker. That is probably what it will do for the inversions that we have today. So I think it's important to have 1 degree, even if you believe that the magnetic field should be very, very small. I think sometimes it's better to just have it as a free parameter because the code can even, in fact, make it weaker. Maybe you have 50 Gauss because you think that this is a good value for quite some inversions, and then the code decides to put 10. So I think it's good to have one node, and the same for inclination. More than that, I think it's not good, mainly because we only have intensity, and also because it's quite sun. So I don't expect to see the impact of gradients along the line of sight from magnetic field strength or inclination. So I think this configuration is reasonable, and mainly that. So if you feel that we are using too many nodes, I think it's just for being in the safe side, in the sense that even if we only have a stocks high, we can have information of the magnetic field, at least until a certain point, but also because our initial atmosphere has the values that are non-zero, and I think it's good to let the code to decide if it needs to make it weaker or stronger than the initial value that we have. So then I think this is everything that I said here. So just let's go ahead. So then what we're going to do is we read the profiles and we are going to save them with this generic name. And this is because we are going to do it several times. So for me, it's easier to keep the same name for the profiles here and then just read different profiles with IDL and then write the profile that I'm interested on that specific instance with the same name. Otherwise, you need to always change the name here. That I think it's also doable, but for me it's easier to just modify the profile inside IDL or maybe Python, and then just write the profiles. And as always, remember that I prepared different routines to write, read profiles and atmospheres in Python, and you can find them in this link. Okay, so just follow this script, but if you want to do it in Python, it's going to be very, very easy. Just translate these sentences and also use the functions and routines that I prepared for these tutorials. So then, with everything ready, we have that we are going to embed the profile at assuming a heliocentric angle mu equal 1. We run the code as always, and remember that the profiles will be a .per file, but it will have the name of the initial atmosphere. Let's go 1 second to the control file. This is the initial atmosphere. So then the profile, the output profile will be the same name and then dash the last cycle of inversion, and the same for the atmosphere. So we are going to read it to use it later. Okay, so then let's check how the code fitted the atlas using the configuration that we have before. I created a lot of plots. I put them on figures, so we don't need to keep running the code now, but in principle, if you run the script in IDL, everything will be generated. So let's go to invert test 1, and this is what we have from the inversion. So the black profile is the atlas, the input, and the red intensity profile is the result from the inversion. So we can see, and I will explain it in detail in the script, but from my point of view, this looks nice in the sense that we have a good shape of the line 6301 and 6302. Line core intensity also looks nice, but the problem is that if we look to the continuum, we see a large discrepancy. This is almost 0.05 in intensity, and I think this is not valid. So in the sense that if you can get a very accurate fitting, it's okay sometimes, but in general the continuum should work very well. So if you don't get the continuum right, then either your calibration has a problem or your configuration is not working correctly, because usually the continuum is the easiest thing for the code. So then what is happening here, and this is what we are going to do now, is that the problem is that we have telluric lines in the inversion. So we are inverting the complete black profile. So we have the telluric lines, and they are waiting during the inversion. And the problem is that we are not given any information of these lines. So the code is not certain of how to do this thing. So if these telluric lines, they were closer to the line, in fact, the code could assume that is some solar phenomena that is happening in the iron lines, because this is the information that we are providing the code. So we are only providing 2 transitions, but we have here 4 lines. So essentially the code does not know how to deal with this. And then the best thing we can do is to just remove it from the inversion. So then the code will always see just 2 spectral lines, and we have 2 spectral lines information in the lines file. Okay, so then let's learn how we do this. The idea is that there are several ways we can think about how we do that, but I think the easiest way is the one that I'm going to present you in a few seconds. But the important thing is that if you said, okay, maybe we can just put the wavelength vector from here to some point here and then continue the wavelength vector. So using like this example, so maybe 2 lines where we have certain wavelength vector and then another wavelength vector, and we cut in the middle. But the problem is that SER doesn't allow to have 2 different lines with the same index. So then the best thing that I recommend you to do is to just keep the original profile. But what we are going to do is to give like 0 weight to a specific wavelength range. So the code will not take this wavelength into account, in particular the telluric lines. So the way we do that is to just set in, for example, the intensity and the force Stokes profiles to negative values. So if the code sees that a wavelength point has an intensity that is negative, but that by definition the intensity is positive, so then the code will just omit this wavelength point. It will not consider it during the inversion. So for that, just let's make a simple plot. In this case, I'm plotting the atlas again, and then I'm plotting here at index 400, 550, and then 830 and 940, I'm plotting vertical lines. So are these lines that we see here, okay? These two and then these two. So what we are going to do for removing these wavelength points from the inversion is just set all the intensity for these wavelength points to -10, and also for the Stokes Q, U, and V. So every time that you do this, then the code will not include those wavelength points in the computation of the chi-square value. So essentially, the code will not try to fit them. And then this is what we need. So then what I do next is just, as you can see, from this point to this point, I set it to -10, and then we save the profile. And just before I forget, if you see in detail, just let me make this bigger. Here it's clear that I'm removing the telluric line. Also, it's important to notice that the iron line probably reaches a bit farther, but it's better to remove wavelength points from a solar line that is affected by a telluric line that we are not considering than keeping them, because it's just a few wavelength points. And the important thing is that we are not able to model the telluric lines, at least we are not including the information in this inversion. So then it's better to lose these wavelength points here that are from the iron line than including this telluric line, because the code cannot handle it. And then what I was going to say is that here it's clear that I'm putting this line just at the end of the telluric line wing, but here I'm just extending it a bit, and the idea is that this is because if you see there's a small bump here, and this is a solar transition. So I think it's oxygen one. I need to check it in detail, but the important thing is that it's not iron 6301, and it's not a telluric, but it's not a line that we have specified in our lines file. So I think sometimes it's better to just remove these wavelength points if you're already removing some of them, because again, if something happens here, if this line for any reason sees an event in the sun that maybe is deeper, or maybe Doppler shifted, or maybe it can produce polarization signals, then the code will try to fit that, but using the atomic information from one line that is not that one. So again, the code will have issues to fit it. So just remove it. We are again maybe losing some points from the 6301 line, but we have all this continuum and all the wings, and the same for the 6302 line. So it's important to remove wavelengths that you are not using actively during the inversion, and they are produced from different elements, so either telluric lines or either solar lines, because the code will not be able to fit them properly, and it will confuse the code, in fact. Okay, so then we set everything to -10. We save again with the same name, and we run the inversion, and then we read the results. In this case, before the variable, I call it SII, SII, SQI, SUI, and SBI. And then now I'm calling them SII1, SQI1, SUI1, and SBI1. So we are only using intensity, but just to show you that we are loading all the results as with different names, so we can compare them later. So then in this case, we are now going to check inversion test 2. And here I'm plotting the atlas, the first inversion, and now the new inversion without telluric lines. So let's take a look. And now the important thing is that the atlas, I'm plotting it with squares and not lines connecting them, because as we set several wavelength points to -10, then the profile, the original one, is going down to -10 and then going up. and then here again going minus 10 and then going up. So I just plotting squares and limiting the y-axis to 0 to 1, but in principle these wavelength points, they are now, and the intensity here is minus 10. So then red is the previous line. You can see that the continuum was not well, but now with the blue line, that is simply the same configuration, but just removing these regions with telluric lines, then now the code is fitting the continuum with much higher accuracy. So then this is a simple, the only difference from before. Removing wavelength points that have features, but they are not belonging to the spectral lines that you have in your line files is crucial for getting good fits. So then now that we have this point, I think this is more or less what I wanted to say. So now let's go to the topic of this tutorial, that was check how different are the atmospheric parameters for a case where we correct for the effect of the limb darkening or not. So then for the comparison, we have that in the previous case where we examined the consequences of having or not the telluric lines, we were inverted the profiles at heliocentric angle mu equal 1. So we have that already. So now let's check the inversion of the profile rescale to mu 0.71. That is what we have here. Now I already removed the telluric lines because we know we have to do it. And then the results will be with the index 2. So without telluric lines and mu equal 1, it's temp 1 and tau 1. And then heliocentric angle 0.71 without telluric lines, so it's a good result, it's temp 2. So now we are going to compare temperature 1 versus temperature 2. So if we open the PDF, we have now that the red corresponds to the case of where we took the atlas and we just normalized to the continuum, the local continuum intensity. And blue is the case where we added a renormalization scale, assuming that the heliocentric angle was 0.71. Okay, so then basically what we have is that temperatures are lower, and this is because the continuum is also lower, but we see some difference here also, and then here the code also we have discrepancies, but here the sensitivity of this line is not very high. But the important thing is this case. So we have that in order to reproduce lower continuum values, the code essentially needs to lower the temperature at lower heights. So then what I'm trying to explain here is that if you have an observation of given a heliocentric angle, for example 0.71, and you only normalize to the local continuum intensity, the temperatures that you are going to get as the continuum is 1 are going to be close to the red line. But as we saw the other day, when you get to the limb, the continuum is decreasing, and also the lines are getting usually shallower. So then the correct one is the blue one, for example for mu 0.71. So if you don't correct for that, you will get hotter temperatures than the one you are really obtaining, and this is simply because you are not considering this effect. So then you need to normalize to the local continuum intensity, but also rescale to the correct heliocentric angle to get accurate temperatures and probably also velocities, but mainly temperatures. Otherwise, you will get good fits, but the temperatures will have an offset because it's not the same to have a continuum in average close to 1 that in average close to 0.8, for example, simply because of the effect of the limb darkening. So then, just as a summary, so in the previous class, we learned that we take a specific profile with a continuum and we normalize all the profiles that we have observed to the average continuum intensity from a Quaternion area. Okay, so we take a Quaternion area, we compute the average profile and the average continuum intensity there, and we normalize all the profiles to that average continuum intensity. But this is just to normalize to the local continuum. But then we also need to include the effect of the limb darkening. So if you are very close to mu equal 1, very close to this center, you will not have an effect. But if you are far, for example 0.7, 0.6, then there you have that your average Quaternion profile, the continuum should not be 1, it should be lower. If we fail to include that, our temperatures are going to be off. If we do it properly, then our temperatures are going to be probably lower, but much more accurate. So then this is the key message of tutorial 1 and 2. Plus that we need to remove wavelength points that do not provide information and in fact can confuse the code, because if we have a solar transition that is not described in the lines LTE file, or we have a telluric line that is not described in the lines file, then the code will try to reproduce the spectral features that those additional transitions produce, but modifying the atmosphere towards changing these lines and reproduce those external perturbation. And this is almost impossible in the case of telluric lines, so then the code was not able to fit the continuum. And if the lines are very close to the transition of interest, then it can introduce very large gradients in temperature or velocity or magnetic field. And this again is also wrong because it's due to other elements, another transition, or maybe the effect of the Earth atmosphere. So then be careful with the normalization and also be careful with the wavelength points you add. Sometimes they can add information, sometimes they can make more difficult to get good results or in fact produce wrong results. So then with these two things, you have everything ready for starting inverting observations, for example, from the KISS VISP or similar instruments. And in the next tutorial, we are going to continue in this direction. But what we are going to do is that in some cases, let me bring just this reference figure. So in some cases, the lines are so broad, mainly chromospheric lines, so for example, calcium 8542, that sometimes we don't reach the continuum. Maybe mainly if we are using filter graph instruments. So we just maybe have spectral points in this part, assume that this is a very broad spectral line, but we don't reach the local continuum. So then the question is, how do we normalize to the local continuum? That is what we have done before, and then include the effect of heliocentric angle if we don't have the continuum itself. And this is what we are going to examine in the next tutorial, that I think is very, very useful, mainly for people that are already using SST CRISP data and maybe IBIS data, that usually with filters you don't go too far, at least you don't reach the continuum in very broad lines like calcium. And I'm going to present you some alternatives to overcome the limitation of not having the continuum, to have a much more accurate normalization than in the case of normalizing to the continuum of the wind, assuming that this is the continuum, because in that case you are going to really have an offset on temperature and very wrong results. Okay, so then stay tuned for the next tutorial. I don't know if you can understand me very well. I believe my pronunciation is not so good, but still I'm trying. I'm getting used to the braces, and I think it will be easier and better in the future. But for now, I just want to say thanks for your attention and see you in the next episode. Okay, bye.